So next up, what I'd like to do is take our conversion from the rectangular coordinate system to the cylindrical coordinate system and apply it one more time. And by that application, I mean the following. Suppose that you have something in 3 dimensions that's already represented using cylindrical coordinates. So we'll go back to that nice made-up RZ thing that I was talking about earlier. Now, technically, the R-axis is not something that exists. It's an imaginary axis that sits within the xy plane. So suppose that rather than creating a reference triangle by dropping it down to the R-axis, consider dropping it down to the Z-axis instead. That'll create an angle over here and a new distance over here. So technically what we would have is, this is a Z value, this is an R value, and we're going to introduce 2 new quantities. Those quantities are going to be the Greek letter rho. And that is going to be the hypotenuse of this reference triangle that I just created. So this is the distance from the origin to the point. Technically it should be displacement, but it's always possible to define rho in such a way where it's always positive. So hypotenuse is rho. And this angle right here, we're going to give an angle name. That is going to be phi. So that'll be the angle between what we have labeled as rho and the z-axis. Now, we are going to throw restrictions on these 2 quantities by saying that rho is going to have to be a non-negative quantity, and phi would start at the z-axis and start rotating in the, I guess that would be, well, from our perspective, the clockwise direction. So the positive z-axis would be an angle of 0. The xy plane, or r-axis in this case, would be at pi over 2, and then straight down would be pi radians. Now, if we wanted to go beyond this way, do keep in mind that we could just rotate where our r-axis is and rotate down in that fashion. So, with those 2 things in place, here are our polar conversions. Essentially, it's going to be the same sort of right triangle trigonometry as what got us cylindrical coordinates in the first place. So, from the perspective of phi, z would be the adjacent side, r is the opposite side, and rho would be the hypotenuse. So it translates in the following fashion. Z is equal to rho times the cosine of phi. R would be equal to rho times the sine of phi. Additionally, we would also have that r squared plus z squared is equal to rho squared. And finally, that the tangent of phi would be equal to the opposite side over the adjacent side. Now, this coordinate system takes things that are round in your round coordinate system and makes them round. So if you start with a rectangle and you make it round once, you get a cylinder. If you start with a cylinder and you make the cylinder round, then what you have is a sphere. This is referred to as the spherical coordinate system. So essentially what we did is we took the 2 distances, r and z, and we converted those into 1 distance and 1 angle. Just like the conversion from x and y into r and theta, we have converted z and r into rho and phi. So that means that in our rectangular coordinate system, an ordered triple would be x, y, z. Taking the x and y and converting those, we would have r and theta in place of x and y. Then what we just did is we left theta alone, and we took r and z and converted those into rho and phi. Now, my understanding is that usually you just let the angle stay where it was in the first place. However, it does vary from textbook to textbook the order in which you put these 3 variables. I'm going to double check ours and make sure that I'm putting it in the appropriate order. Now with that in mind, This is how we would convert from cylindrical coordinates to spherical coordinates when we already have access to all three of these quantities. Now, if we wanted to go straight from Cartesian into spherical, that would look a little bit different. Now, that would look like the following. When we converted once, x was equal to r times the cosine of theta. But now we have a conversion for r. So that would be rho times the sine of phi times the cosine of theta. Cool. Y was equal to r times the sine of theta. But once again, we have a conversion for r now. And the conversion for r is that this is rho times the sine of phi times the sine of theta. And finally, z in its current form is already in terms of just spherical coordinates, so we can go ahead and leave it as is. Now, additionally, this lets us know that we also have that x squared plus y squared plus z squared is equal to rho squared by taking this and converting in what r squared is equal to from polar coordinates. We also have that let's see, we could do, I suppose we could do either one of these, or we could do this one down here, but as far as phi is concerned, we could do the tangent of phi is equal to, we said r over z, and as long as we're defining r in a positive fashion, which we tend to do anyway, you could make use of this. Typically what I would encourage you to do is use the definitions of z and r and rho to figure out what the sine and cosine of phi would be, and then simply figure out phi from that. In our next video, we'll actually start talking about some surfaces within the spherical coordinate system, but spoiler alert, they're mostly going to be spheres.